Hi everyone, welcome back to Algorithm Simplified. Today we're going over Leetcode 2218, which is maximum value of K coins from piles. Let's begin by reading the problem to figure out what sort of approach and what sort of problem this is. There are n piles of coins on a table. Each of these piles consists of a positive number of coins of assorted denominations. In one move, you can choose any coin on top of any pile, remove it, and add it to your wallet. Given a list piles, where piles I is a list of integers denoting the composition of the ith pile from top to bottom, meaning index 0 until the last index, and a positive integer k, return the maximum total value, so maximizing, of coins you can have in your wallet if you choose exactly k coins optimally. What does this mean in an example? Let's look at example 1. So here we're given a 2D array piles of the following, and k, 2, meaning we pick 2 coins. In the above picture, we see all the possible ways we can pick 2 coins from these piles. We have to select what's on top because these are piles. So the first possibility is that we choose 1 and 7, the tops of both piles, giving us an answer of 8. The other possibility is that we choose the first thing on the second pile, allowing us to get to the second coin on the second pile, giving us 7 plus 8, 15. The last possibility is that we choose the first coin in the first pile, and then exposing the second coin in the first pile, we choose that as well. Our answer is 101 because this is the maximum such combination. Now that we have read and understood the problem, let's see if we can identify key elements about the nature of this problem to figure out what sort of algorithm we need to implement. Here I've written down 3 things that I find are key to the nature of the problem. The first is its recursive nature. We can see that we can build up an optimal solution piece by piece from smaller chunks and combining them together to get an optimal solution. What do I mean by that? Well, I can make a problem so that instead of looking at n piles, I can look at n minus 1 piles with k minus 1, all the way to 1 coins. And I can keep breaking this problem down and down into smaller and smaller pieces until I reach where I find that optimal solution for our k coins for our piles. The second thing about this is that there are a lot of overlapping subproblems. In my prior approach that I just explained in recursion, for any pile that I'm on, I can break this problem down into smaller pieces where all prior piles can have either k coins, k minus 1 coins, all the way till 1 coin to take. And we can see that there might be a lot of overlapping subproblems there if you consider that you need to do the same thing with any of the prior piles there exists. Right away, these 2 factors remind us that we probably need to use dynamic programming with some sort of cache. Finally, this is a maximization problem. We can see that very clearly by this bolded text that tells us to return the maximum total value. In terms of dynamic programming maximization problems, which are called MaxDP problems, there are 2 types. The first implements a greedy algorithm, where we choose locally the best or most maximal solution. And the other one is called the Knapsack problem, where there is backtracking implemented with a cache. Let's see if greedy works. Well, judging by our example right here, we can see that greedy doesn't work. Locally, we can choose either 1 or 7 for our first coin. Since 7 is bigger locally, then we would choose 7, giving us an option between 1 and 8. This would prompt us to choose 8 to maximize our output since 8 is greater than 1, giving us an answer of 15 when our correct answer should really be 101, pointing us towards the fact that greedy is not the correct way to go, but that we do need to use Knapsack. Personally, I find that the most difficult part about this problem is translating Knapsack into a correct implementation for K coins. Knapsack inherently takes different structured inputs than K coins. In Knapsack, we're asked to maximize the value given two 1D arrays of equal length, weights, and values. In K coins, we're asked to maximize the value given an integer K, indicating our number of coins, and a 2D array piles, where each pile array within piles is unequal sized. In Knapsack, at any I indicating the element we're currently on, in C indicating how much weight we have left in our knapsack, we have two choices. We can either take what's at element I or not take what's at element I. If we take what's at element I, we add the value of I to our total value count, increase our I to the next element, but we need to subtract the weight of I from what we have left to carry in our knapsack. If we don't take I, we just simply move forward our I counter and keep the same C. What's similar about that for K coins is that we do indeed have the same structure. When we don't take from pile I, the structure is very similar to knapsack. We simply increment I plus 1 and keep the same K because the same number of coins still need to be taken. The difference, key difference, is what we do here when we do take from pile I. What we need to do is we need to do a loop through every single element in our pile I. So for every single element in pile I, let's denote that J. At some index J, what we need to do is we need to calculate I plus 1 and then K minus J minus 1. Starting from index 0 until the end of our index for pile I, we are at some jth coin. What this means is that so far we've taken J plus 1 coins from the top of pile I plus 1, moving on to the next pile, and K minus J minus 1, meaning K take away how many coins we have already taken from our pile, which would be J plus 1. So K minus bracket J plus 1 is K minus J minus 1. And we need to add the sum of all the coins from 0 till J so far. Before I go into the code solution and big O analysis, I invite you to try and code this out on your own. So pause the video and come back. Okay, now that I've assumed that you've already taken the time to try this out yourself, let's go over the solution. So first what I do is I differentiate between capital K and N, which means the K we were given and the N length of piles, as opposed to the small letter n and small letter k, which are local to each knapsack recursion. Capital N denotes the length of the piles, while capital K denotes how many coins we are given. I initiate a cache for dynamic programming, where I make the value -1 to denote that it hasn't been visited yet or it hasn't been calculated yet. I make it two-dimensional with k plus 1 and range of n plus 1 because the number of coins and n are inclusive in the way that we have approached this problem. So for knapsack, our implementation, what we do is we check our base case. Have we reached the last pile? If we reached past our last pile, we simply return 0. You'll see why in a minute that I do not need to include a base case for k. Let's move on for now. If the cache is not -1, or if we've already calculated for this nk of our knapsack, we simply return what's in the cache. Again, there are two options, very similar to knapsack. Option 1 is that we exclude. We don't take from pile small n. And what we simply do is we increase n to the next pile and keep the same number of coins that we need to be finding. Option 2 is that we do indeed take from pile n. What we do is we create two variables, and this is where it differentiates from the original knapsack problem. Include is initialized to be 0 as a starting point, and value of coins from pile shows us the total aggregate sum of all the coins values that we've taken from pile I so far, or pile n so far. I is the index referring from index 0 all the way till the end of pile n, pointing us to which coin is on top so far. What we do here is pretty clever. We take the minimum of k and the length of piles n. Why do we take the minimum? Well, if there are less than k coins left in our piles n, then we can't take any more. For however many k coins there are, we need to move forward to the next pile to take from. If there are more coins there are than in k, we don't need to calculate that because we are only limited to k coins for finding how many coins or the maximum value in total. So by taking the minimum between the two, we guarantee that we don't need to consider the base case for when we have a k that is less than or equal to 0 for no coins left. So what we do is value of coins from pile needs to be updated to add in the value of the current coin ni. The value of include gets updated to the maximum between itself and the current value of coins from pile that we've just updated, plus the knapsack of n plus 1 k minus I minus 1, meaning we take I plus 1 coins from piles n. This is our value so far. And in the end, we update our cache to have the maximum between the exclude and the include, whichever one gives us the maximum, and we return the value calculated. At the end, we just call for returning of knapsack starting from the 0th pile, taking in capital K. In terms of memory or space, for big O, we have O of n times k, as you can see by the cache here. Even though it's a k plus 1 by n plus 1 cache, in big O notation, that's n times k. In terms of time complexity, what we would have is O of m times k, where m is the total number of coins in our piles. So in other words, the aggregate sum of all lengths of subarrays within our two-dimensional array piles. Why is that? Well, for every single knapsack state, we need to consider taking all possible coins from the piles. And since we have to do this for every single k that we're given, for every single coin in the pile, therefore we have m times k for the time.